Hello, welcome to the session on Microsoft SQL Server Basic Data Structures. I'm Christopher Richard, Managing Director, Chief Software Architect, G7CR Technologies, India Private Limited, and pretty happy today to take you through this session on behalf of Microsoft. I really hope you're going to enjoy this learning experience as much as we've enjoyed making this video for you. Getting started with our topics today, we will try and cover for you as clearly as possible the communication architecture, the instance architecture, the database architecture, data file architectures. We'll go down right up to the page architectures, and we'll also introduce you to data structures and indexes. Now that's the agenda for today, so sit back, relax, and enjoy this video. The first architecture we're going to cover this in this session would be on the client-server communication process. What you're looking at on the slide is the client application, which needs a driver. It needs either a native driver or a third-party driver in order to communicate with the SQL Server instance. Now, the driver's role here is to convert any message or any query that you're actually trying to pass to the server, or any command you're trying to pass, into a format in which SQL Server could understand and interpret it. SQL Server uses a native protocol, which is referred to as known as the Tabular Data Stream Protocol, or the TDS protocol. So what your provider does when you're using the native driver is it picks up your command, applies the rules of how this message is supposed to reach SQL Server for interpretation. In other words, it converts this message into a TDS packet, and later on passes this packet to the client net libraries, which decides based on your configuration how it is going to, which network protocol it's going to use in order to pass this TDS packet across to your server. Now, before we actually go into this and look at what happens after that, I'm just going to take you into a small little demonstration showing you how you could configure the client network utilities in order to basically use the network protocol of your choice. All the labs in this session have been done using virtual machines, so I'm switching over to my Azure virtual machine here. Just give me a second for that to basically come up. Got a black screen there. That's because I've been connected for long. Just give me a second and we'll be up and running. There, I connect to my Azure virtual machine, and I'm doing a remote desktop to this machine which has SQL Server 2014 instance installed on it. Before I go into the SQL Server 2014 instance, I'm going to open up the SQL Server 2014 configuration manager for you. And assume you're going to do this on the client machine. You have something here, you have a utility here called the SQL Server native client configuration. Now, in the native client configuration, you have the client protocols that are currently enabled on the client machine. Now, if you're looking at the protocols currently enabled on this particular machine, you can see we have shared memory, we've got TCP/IP, and we've got name pipes. We've got all of these three protocols enabled. Now, please remember, this is the client configuration. You need to configure this on the client machine. The interesting aspect of this right now is the choice of which network protocol to use is always made by the client who's making the request to the server. It is never decided by the server instance of SQL Server. For example, right now if I try to make a communication based on this configuration which I've basically got on this machine, it would first try to use the shared memory protocol. Why? Because you see, we have configured that as the order number 1. So the first attempt will be made to use shared memory. In case for some reason it's not able to communicate with shared memory, it will then go ahead and try to basically make a connection using the TCP/IP protocol. And if it's not able to make a connection using TCP/IP, it will then try the third protocol here, which is named pipes. Now, the shared memory protocol is an interesting one. It can be used only in scenarios where the server and client are both located either on the same physical machine or a virtual machine where the server and client is both on the same box. In this case, that's the way it is. So we would be using shared memory most of the time. But there could be a lot of scenarios in your production environments where that's not the case, and you would most probably save yourself quite a bit of time here trying to attempt a protocol which you cannot use. For example, shared memory cannot be used across machines. You'll have to use them in the same machine. Now, what you could do is, in case you're sure of this configuration, where you are trying to communicate, the client is trying to communicate to a SQL Server instance, which is on another physical box, you could go straight ahead and disable the shared memory protocol from here, thereby making TCP/IP the number one choice. This would mean that your client application now would first try the TCP/IP protocol and not the shared memory. You can also go to the right click order and you can rearrange the order in which you want the client to attempt the network protocols that need to be used. For example, TCP/IP or name pipes. You can see these arrows here which will allow you to make the changes or move the order up and down, changing the order from 1 to 2 to 2 to 1, or however you think most probably feasible. I'm going to go back again here and enable shared memory, because on this machine my client and server is on the same box, so the recommended protocol here would be shared memory. So I will go ahead and enable that back again so that it becomes the first protocol that my client would try. On the other hand, since this machine also has an instance of SQL Server running, I have here the SQL Server network protocols. And when I click on this, you will see I've got the shared memory enabled, I've got the named pipes disabled in this instance, I've got TCP/IP enabled. So this actually means that if my client for some reason never used TCP/IP and choose to use named pipes, my server will not be able to respond to that network request, because we do not have named pipes enabled on the server. So if you're trying to understand this whole flow, the client makes the choice of the protocol. Using that protocol, the message is sent to the server. Now on the server, if you have that protocol enabled and if it's listening for requests, it would receive that message and it would respond to you in the same protocol that you used to actually make that request. So this is the configurations that you could basically play around with when you're actually working with the communication. I'm moving back to my PowerPoint slide right now. And this was where we've seen a TDS packet gets created by your provider, your database API, your OLEDB provider, your native driver. The TDS packet is then passed on to your client net utilities, which decides which protocol it needs to use to try and reach the server. And this is driven by what you've seen just now, where you need to basically set up that configuration. Now once this reaches the server receives these network packets, it does a handshake with your client, tries and ensures that your components, that all the components were received and nothing was lost during the network transfer. And once it's sure of that, it assembles back these network packets into a TDS packet and passes it on to Open Data Services. Open Data Services will now interpret your query, pass it to the relational engine, and this is where you have all the optimization. The optimizer comes into play. It passes your query, breaks up your query into small little parts, optimizes the query. Once the optimization is done, it basically chooses, it creates a plan of how to basically execute this query. That's what we mean when we say optimization. It chooses the best plan and compiles that plan and stores that compiled plan in a procedure cache. And then it goes ahead, passes instructions to the hardware, your processor, your memory, your storage engines, retrieves whatever data you need to be retrieving, and returns that back to Open Data Services. Open Data Services converts this back into a TDS packet and passes it back to your client using the same network protocol which you used when making the request. Again, this is received by the client. Again, a check is made to see that nothing was lost during the network transfer, and a TDS packet is assembled again, passed on to your native driver, which interprets that TDS packet and passes on the results to your client application. Now, this entire concept of communication which we are talking about is how you actually is the components that are involved when you're trying to connect or talk to the server, either on the same machine or on a different machine. An interesting thing about this picture that you're looking at here is open data services, relational engines, the storage engine, and the optimizer, and lots of other components that are involved in the SQL Server instance. All of them today run on what we call the SQL OS. Now, the SQL OS is Microsoft's attempt to try and communicate as much as possible directly with your hardware, bypassing Windows in many more cases than the earlier editions and versions that SQL Server used to use. So most of these components which you see on the server side run today on what we call the SQL OS. Now, this was the first part of the communication architecture. I'm going to take you to the second part of the communication architecture, and this I'm going to do for you with a demonstration where I'm going to show you what exactly schedulers do and what is the role of a scheduler and how it actually works. Now, when I right click on this task manager here of my machine, I'm going to go to the performance tab for you, and I'm going to show you currently this virtual machine that I've configured. It has one socket, that means one CPU, and it has two virtual processors. Now, these two virtual processors could actually be two cores on this CPU that this machine has, or it could be hyper threads in case you're basically working with Intel based processors, because hyper threading is something which Intel based processors uses pretty often. For example, today if you're using an Intel i7 desktop, you would most probably see 8 virtual processors there, which means you have 4 cores, and each core has 2 hyperthreads, making it 8. Now, why am I giving you this information? Because you see here, you see 2 virtual processors, and now I'm going to open up the SQL Server Management Studio for you to relate that information. So I'm going to open up the Management Studio, give that a second for it to basically open up on screen. And I'm going to connect now to my instance which is installed here. I'm going to go to the properties of this instance. I'm going to go to the processors here. And what you would notice now when that screen throws up, you would notice that we have a NUMA node, and NUMA is the architecture which ensures that there is no contention for shared resources today. So the NUMA node controls the allocation of resources to the multiple CPUs that you could have on the box. What is interesting here is I've shown you 2 virtual CPUs on this machine, and SQL Server assumes that each of those virtual CPUs are actually CPUs. In fact, when SQL Server is communicating, when he's building execution plans, when he's trying to basically use multiple CPUs, he's going to make a presumption that you've got SQL Server installed on a machine that has 2 CPUs. Although I think technically if you look at it, we know that we have only one CPU on this machine and most probably 2 cores. Just like the example I gave you about the i7 machine, if you install SQL Server on an i7 machine, you would see 8 CPUs there, because each hyperthread will be treated as an individual CPU. Now, some configuration that you could actually do here is you could change the maximum worker threads for each of these CPUs. You will notice the default here says is 0, and 0 actually means here that unlimited number of worker threads could be generated by the system on this particular CPU. Now, the way SQL Server works, when you want a request executed and that execution plan is built and instructions are passed to the CPU, it is passed to one of these CPUs. Now, these CPUs in turn will create worker threads to execute those tasks which you assign to it. Now, how many worker threads are required for the task depends on the task. You could have tasks which need maybe a dozen or need hundreds of worker threads to complete, or you could basically have tasks which most probably have only. I rather won't use the word task here. I'll use the word command. So they might be a single command, but that single command could be broken up into multiple tasks, which means you need multiple worker threads in order to complete that command or execute that command successfully. So what can be configured here is the number of worker threads. Now, normally, if you have unlimited and SQL Server runs out of worker threads and you keep on passing no new commands to the CPU is going to throw you a lot of funny errors. He's going to tell you that I cannot create worker threads anymore because I don't have the resources to create it. So in case that's happening to you, you most probably need to come in here and reduce the maximum worker threads that you're allowing, so that SQL Server stops attempting to create worker threads when he reaches the max. I cannot really give you a best practice number here because this really depends on the kind of workloads you're running and the kind of resources that you have available for these worker threads to get created. Interestingly, this is SQL Server making an assumption of the number of CPUs that you have and using these CPUs, which in turn create worker threads in order to execute those queries for you. You do have a concept here to boost the SQL Server priority. Now doing this will actually mean that the SQL Server tasks will be given a higher priority than the general priority given to most applications that are running on Windows. This is a dangerous thing to do, so I would not recommend you do this because it could mean that some of the SQL Server jobs would basically take priority over some of the Windows jobs, and that could create some critical stability issues on your machine. So leaving that out is most probably the best practice. Don't try to boost the SQL Server priority on Windows. You can also use lighter weight threads in case you're running out of resources, but I would recommend before you check that box and try to use that to please go through the documentation and try and understand all the limitations of using lightweight threads. For example, you cannot use the CLR when you're working with lightweight threads. You cannot use extended procedures when you're working with lightweight threads. So the series of other limitations. So recommended go through the books online on limitations of using Windows fibers before you actually choose that option. The reason why the option is available, in case you have the regular threads are having a problem with resources and you're not able to create sufficient threads, you might like to convert that to fibers because fibers are more lightweight threads and use far lesser resources than the normal threads which are created to execute your tasks. However, everything comes with a rider. There's no free meals here at all. So if you're going to go that way, you will have to remember there are going to be certain limitations of certain things and certain commands which will not run on a fiber. So please look that up and only go for this option if you're sure that your application doesn't use those commands and those limitations will not be limitations to the application you're talking about. Now that's the external perspective of CPUs and threads and how it actually works. Now from the internal perspective, SQL Server doesn't know a CPU. What he does know, or what he does talk about, is what we call a scheduler. Now let me just show you the schedulers that SQL Server has. I'm going to say sys dm underscore os underscore schedulers. There you go. Let me execute that command for you and you will see a series of schedulers that are currently available on your machine. Now in the schedulers that's available, the ones that are important to you are only the ones which have a status of visible online. The reason being, those are the only ones you could use. You cannot use schedulers which have a status of hidden online because they are used internally by the system and you will never be able to use them for any of your tasks. So let me just remove that there and you will see that we have only two visible online schedulers. Now these schedulers are bound to my CPUs, that is CPU 0 and CPU 1. So when you make a query on SQL Server or when you make a connection, we are talking about the communication architecture here. When you make a connection to SQL Server needs to pick up that connection which you're making and bind that connection to one of these available schedulers. Now these schedulers are actually bound to CPUs. So when I talk about binding to an available scheduler, it means I'm actually binding you to a particular CPU which will be responsible for the tasks you're submitting to it. So the CPU now is, we are going to refer to it as schedulers because that's what the system calls it. So I've got my scheduler here which is bound to this CPU. I got another scheduler here which is bound to this CPU. So when you make a connection, Microsoft SQL Server needs to decide which of these two schedulers is he actually going to bind your connection to. He makes that decision by looking at the workload on that particular server, which you see right now, which I'm highlighting for you. It is called the load underscore factor. So he looks at the load factor on each of these schedulers and he assigns your connection to whichever scheduler at that point of time has the lowest workload. Now, once you're bound to the scheduler, any commands which come, the evaluation of that command, the optimization of that command, the compiling of that command will all take place using the scheduler which you're actually bound to. However, the execution of that command could happen only on this scheduler or could happen on multiple schedulers depending on whether that task was a serial plan which is getting used or a parallel plan. Now later when we are doing some more videos, we'll talk in a little more depth about how plans are created in optimization when we are working on the performance tuning session. So right now I'm going to leave that out, but do understand you're bound to one scheduler. You pass on that a command to that scheduler. So what really happens is the parsing and the compiling will take place on that scheduler. But whether that command is executed after being compiled on that single scheduler or multiple schedulers purely depends on whether it was a serial plan or a parallel plan. Now the interesting thing is, maybe at connection time, the scheduler with the lower workload may have been scheduler 0, and I get bound to the scheduler. Let's say I get bound to the scheduler 0 because at this point of time, this had the lowest workload. So I pass in a command, the command goes to the scheduler, worker threads created on the CPU, the command is executed. Or the command is still in process of execution. I make another request now. I make another command right now. SQL Server will check again to see whether there are any schedulers which have a lower workload than the one you are currently bound to. And you would move, and it would move your connection to that particular scheduler, leaving the tasks and the worker threads of the old command to continue to run on the current scheduler. However, the new command will automatically go to the scheduler which has the lower workload. So this actually means you're not really tied up to one scheduler no matter what happens. Every time you execute a command, SQL Server checks to see if there are other schedulers available with lower workload factors than the scheduler you're actually bound to. And if this is true, you would move your connection to that particular scheduler. Now, another interesting thing which we could basically learn at this stage would be is I'm going to change this command here from where to equal to. I'm going to say where status like visible online, and I'm going to put person there and execute. Sorry, and execute. And you'll notice I land up with another scheduler here. This is the third one. Earlier, visible online, we had 2. And you can see I've got another visible online, but the difference here is in brackets, you see something called DAC, which is basically written to it. You see DAC or DAC. Now, this is a reserved scheduler. It is reserved. You cannot use it normally. Your normal connections will not even look at this scheduler. It will only use the ones with status of visible online. It will not look at this scheduler because this scheduler is reserved. And it is reserved for usage of what we call a dedicated administrator connection. Now you can make a dedicated administrator connection to SQL Server when your system is not responding or your system is not working well, and you want to go and troubleshoot but you're not able to connect to the system. This really means that you're not able to bind your connections to a scheduler. It means your system is not hanging. It means your schedulers aren't working. So by keeping one scheduler reserved, which means it's not being used, it means you can actually communicate to a system that's not responding and try and troubleshoot what's wrong with it using that particular method. Now this is something which was introduced in the SQL Server 2005 version, where administrators got this ability to be able to use one reserved scheduler and create a connection which was referred to as a dedicated administrator connection. I'm going to show you in a second from now how to actually create a dedicated administrator connection, and I'll take you through that in a second. So this is the demo where I'm going to show you how to actually make a dedicated, how to use the scheduler. Now for this you need to make a dedicated administrator connection. So I'm going to go to new, I'm going to select database engine query here, and what I will be doing here is instead of just putting my instance name, I will put in the keyword admin colon and then my instance name. I need to be using a user who has system administrative privileges, otherwise this would not work. Currently on this system, my Windows account has system administrative privilege on this instance, so I have no issues about it. So I select my, just notice here, all you have to do is put admin colon and whatever instance you want to connect to. Now when I click on connect, I've made a connection using the DAC scheduler, that reserved scheduler. So this, don't use this for your normal connections, please. This needs to be used by administrators. You need to have system administrative privilege, and you need to use it only in scenarios where you're having trouble connecting to SQL Server in the normal way, and you'd like to basically connect using this reserved scheduler and troubleshoot that problem. So that's a nice little feature which you have and you can make use of. With this, we've completed our topic on communication architecture. There's a small little quiz here which you can take. If you're viewing this video using the HTML version, you'll be able to take this quiz. Otherwise, it will simply move on to our second subject. So enjoy the quiz. I'll meet you again once you're done with that quiz. Hello. Welcome back, and let's go on to topic 2 of this session, where we're going to discuss about the SQL Server instance architecture. I'll open Management Studio for you, and this is the SQL Server instance that I have installed here. And the SQL Server instance is made up of a series of system databases: master, model, MSDB, and the tempDB. 4 of them which are visible. There's one database which is not visible to you, and that's the resource DB. And we'll talk about each of them, and we'll discuss what they actually contain. Now, when it comes to understanding the instance, these 4 databases are what actually makes up the instance. So when you are trying to visualize SQL Server as an application or as a database, what you need to visualize, of course, there are a couple of EXEs and DLLs which basically will form a part of the application and the engine which basically runs. That's the actual SQL Server service. And apart from that, you have a series of databases which store data, or rather, let me put it this way, stores metadata related to the functioning of the instance. So for this instance to basically work well, you need to ensure that all your executables, which would be in your installation directory, that is C drive, program files, Microsoft SQL Server. That's where I've installed it in this particular instance, MS SQL, and here you can see a series of DLLs which are available for various functionalities that you actually use in the database. You will notice here we've got the database mail exe, which is here. This is an application. We've got a couple of DLLs here for backup. We've got a couple of DLLs here related to all the features that you have in the database. You can see a series of DLLs which are located here. Now, apart from these DLLs and EXEs and applications, which forms the functionality part of the database, what is another important aspect of the instance are these 4 system databases that we just discussed. Now, what these 4 databases do necessarily is store metadata in some fashion or the other. Now, what is metadata? Of course, the most popular definition I've ever heard in my experience on that has been it's data about data, but let's find a proper context to it here in this scenario. When we talk about metadata, it's everything except the actual data that you want to store in your database. When you create a database, the name of that database, the properties of that database, the file names, the configurations of that database, all of this forms what we call metadata. When you create a table, the name of the table, the name of those columns, the data types of those columns, all of this will form metadata. Metadata can be categorized into 3 different types. We can talk about metadata that is related to the instance. Now, when I talk about metadata related to the instance, I'm talking about all objects that you will create on the instance of SQL Server. Example, when I create a database, I'm creating a database on the instance of SQL Server, this particular instance. When I create a login, I'm creating the login on the instance of SQL Server. When I create a server role, which we can create today, you can create your own custom server roles from SQL Server 2014. So when you click on new server role, you are creating something on the instance. So whenever you create objects which are on the instance, the metadata of that objects is what I would refer to as instance metadata. Now, all of this instance metadata is stored in the database called master. This is the reason why master is a critical system database. In case master gets corrupted or you lose the master database for some reason, your instance goes down. Your instance will not be able to function anymore. The reason being is pretty simple, because your logins are stored inside the master. So how would you log into an instance of SQL Server if the master database itself is not available? All other database information, including if I'm able to see this database called credit or this database called Northwind here, these names which you're looking at here is coming from a system table which stores this information in the master. So if I click on new query here and I run a query which says select star from sys.databases, and I run this query, you will see all the databases available. You notice I ran this query in master, so sys.databases gives me all the databases that are basically available and its metadata is stored there. Now if I went to one of the user databases, for example Northwind, and I executed sys.databases, I still get this information. However, sys.databases is a view, and this view is accessible from any database, but actually this information is available and stored in the master database. So the master database becomes the holder of all system metadata, all system related information. I can also show you another system view here called sys.logins. Syslogins. This is a backward compatibility view. It's one from earlier versions of SQL Server. This metadata view is also something which is stored in the master. So all the metadata for the instance, all the objects that you create on the instance are stored in master. The model database simply forms a template for all new database creations. So if I go to the model database and I create a new table here, let's do that. I'll create this column. I'll call this column 1, and it doesn't really matter. And let me name this column. Let me name this table. I'm going to call it Chris. That's my name. So I've created a table called Chris here. I'm closing down this table, and let me refresh this now. So you'll see a new table in the model database. If I right click on databases and say new database, and I create another new database now on my instance called test, what he does is he makes a copy of the model. Now to prove this to you is, if I drill down tables in this new database that I created called test, you will see the table called Chris very much visible there. Now this new database is not permanently linked to model. Model is only used as a template to create this database. I go to the model, I delete the table Chris from the model. If I come back to test and I refresh, Chris is still very much there, because when I was creating this database, he simply made a copy of model in order to create it. But thereafter, the link with model is no longer. If I now create a new database and I call it test1, it will not have the table Chris, because at this point in time, the model database does not have the table called Chris because I deleted it. Here you see we don't find the table called Chris anymore in it. So the model is simply a template for all new database creations. It simply makes a copy of the model whenever you try to create a new database. MSDB is, I find it difficult to explain the MSDB, but I would most probably put it in the most basic and simple way. Now, apart from objects that you create on the instance, for the functioning of the instance like databases and logins and server roles and so on, there is also certain things that you create purely for administrative purposes. For example, I might want to create a job on the SQL Server agent service where this job would most probably need to back up my databases every day. I might want to schedule that job. I might want to create an alert so that I'm alerted when certain things happen in the system. I might want to create an operator who's intimated when things go wrong or when things go right, when things succeed or when things fail. Now all of this also has metadata. Your job, the job has a name, the job will have a description. If you ever created jobs before, you will know about it. So for example, here I will create a job, I will call this the test job. I will go to the steps of the job, and in the steps here I'm going to say I want to back up a database. Here I will say I'll run this command from master most probably, and here I will type in my backup command where I will say backup database blah blah blah. Okay, I'm not typing up that command, but you can type your transact SQL command here, and then you can click on OK to save this job. So I've just created a job right now called test. Now this job had certain steps in it, it had certain transact SQL syntax in it. Now this needs to get stored somewhere. Now this job will get stored in the MSDB database. You also have, apart from jobs, alerts, and operators, you also have when you configure database mails, mails need to get sent. If they fail, the log gets created. If they succeed, a log gets created. So a series of tables are available to store the information about mails, and mail logs are also a part of MSDB. So MSDB stores I would most probably put it in one sentence. I would say it stores all administrative related metadata like jobs, alerts, operators, mail tracking information, and so on. The fourth database is the TempDB. The TempDB happens to be the most happening database in the entire system. Now, if you've worked with any application in the world, any kind of an application which deals with data, you would have understood that this application, even if you're working with Microsoft Office and Word or Excel, the way it functions is there is a storage layer where data is stored on the hard disk, and there's also a layer where data is stored in your memory. It's stored in your buffer. It's stored in the memory while you're working on that data, while you're editing that data, or while you're doing something to that data. Now, lots of applications, in case, let's take a very simple example here. Let's say you had 10 MB of memory with you, and you were trying to open and edit a document which basically was let's say 30 MB. Now the problem here is you have only 10 MB of memory with you. So what happens in this case? Now the document has to be brought to memory because you want to open it up for editing. Now a lot of applications that I know of would have a temporary space on the hard disk which is called the caching area, and it will use this cache in order to put that data there while it's running insufficient when due to insufficient memory, and it'll swap this data in the cache with the memory while you're trying to edit it. Now SQL Server also you have to do a lot of work with a lot of data. You most probably are trying to sort data, you're trying to group data, you're trying to summarize data, you're going to do a lot of operations on the data which is in the databases. So you can read the data most probably from the data files in the database. That's the hard disk. You can read it from the hard disk, bring it into the buffer. What happens if you don't have enough buffer? What happens if you're trying to basically read a table which has 100 billion records? And what happens if you want to sort that table? What happens if you need to do a join operation between two tables? Now data needs to get stored temporarily somewhere. Now SQL Server will use the buffer in order to store this data wherever it's possible. However, in case there is a lack of space in the buffer and it cannot bring that entire data into the buffer, SQL Server will create work tables in the TempDB and store this data in the TempDB. So in one sentence, if you ask me to describe the TempDB database, I would say it is the temporary caching area for SQL Server where he uses the TempDB to store the data when he needs to temporarily store data to run some operations on it. SQL Server will land up using TempDB as that database to temporarily store that data. So having made you understand what the TempDB does, it's a misconception with a lot of people feel is TempDB gets used when you create temporary objects like hash tables or table variables or so on. The truth is, irrelevant to whether you creating temporary objects, internally the system while operating on tables, whenever it needs temporary storage, will use the TempDB. Now that's a good thing and that's a bad thing. The good thing is that SQL Server does have its own exclusive area for temporary storage, which is also a database, which is the TempDB. The bad thing is every instance of SQL Server has only one TempDB. Now, especially I work with a lot of these service providers. If you were one of these service providers who actually work with, maybe you are a shared hosting provider, what would happen most probably is you will have one database for every customer you have, and maybe due to licensing, you would not want to create multiple servers, so you most probably will start having thousands of databases created, user databases created on the same instance of SQL Server. Now, this is the bad part of TempDB because you might be able to create 3,000, 4,000 user databases on the instance, but all these 3,000, 4,000 user databases will go to only one single database for temporary storage, and that is the TempDB. A lot of times we hear about TempDB performance issues, but then the reasons for these issues are pretty obvious ones. We have only one temporary storage area, and that is the TempDB per instance. Now, if you were facing these issues, there are lots of ways of optimizing it. One of the ways is to keep this database as fast and appropriate as possible. And one way of doing that is to create multiple data files for the TempDB. By default, it would have only one, and that's the primary data file. So the recommendation here goes to create multiple other data files on the TempDB and put each of them on separate physical disks, and those physical disks would most probably need to be the fastest your money could actually buy. The maximum number of data files I would recommend you need to create here, they should not exceed the number of CPUs, logical CPUs that SQL Server uses, because you might solve an I/O issue and you might cause a processor bottleneck in case you land up creating more data files than the total number of logical CPUs that SQL Server is using at that point of time. We've already understood CPUs and schedulers, so I think I don't have to explain that again. So the max number I recommend here is do not exceed the number of data files. The number of data files you create here should not exceed the total number of logical CPUs that SQL Server is using on the machine. So that's one way of trying to basically ensure at least the I/O bottleneck related to TempDB is solved. And the second thing, which would most probably do you a lot of good, is if you're a developer or if you're an administrator, you need to start talking to those developers and you need to tell them to stop using hash tables unnecessarily. What I've noticed in my experience, a lot of people land up using hash tables not because they need to temporarily store data for some reason. They land up using hash tables just to basically ease the programming logic, to break up the programming logic into multiple units. Now, this needs to be avoided because since TempDB already has enough issues, has enough temporary storage internally, we burdening it with a lot more hash tables that we create, and especially if those tables were unnecessary, would further cause the deterioration in performance of the TempDB. So these would be some standard guidelines. Apart from all of this, I would recommend that you not look at the maximum number of user databases as per the limitations in the documentation, and try and create multiple instances of SQL Server. And you can do this most probably on the same physical server, so that you don't really have need to spend on another license. So you can install multiple instances of SQL Server on the same physical box, thereby, because every instance will have its own set of system databases, which means you land up with multiple temp DBs, because each instance will have its own, and then you can split your user databases across those multiple instances. So those are some tips and tricks and some recommendations on how you could improve the performance of TempDB. Now, the fifth system database, which is not visible to you anymore, which I'm going to show you actually in this demonstration. I'm just going to go and find it in a minute here. I'll go to Microsoft SQL Server, MS SQL Server, MS SQL, and bin. And what I will do right now here is I will search for the system resource database, which is very much right here. I'm going to copy these files. You can copy this while the instance is running. Okay, so this is the MDF file and the LDF file of the resource DB, the system resource DB. I'm going to go into my data folder and make a copy, paste that copy of that file here. So now I've got another copy now of this. So the original copy stays intact. I'm not touching that at all. And I will attach this resource DB now to my system. So I click on add. I select the MS SQL system resource.mdf. I click on OK here just to show you this error. It says an error occurred when attaching the database, and if you look at the error link here to find out what really went wrong. You will tell you that you cannot perform this operation for the resource database. Now, the reason why the error message is a civilized one, it's one which he wants you to understand, but the actual error or the actual reason why you cannot do this is because the system resource DB already exists on the system, so you cannot attach it again. This database is hidden. It's there. It's very much there. You cannot see it. So this is something like the ghosts, most probably. I mean, it's very much there, but you cannot really see it. So what we need to do most probably to attach this is I will trick the system and change this database name from sysresourcedb to anything else that I want, as long as a database with that same name does not exist. I will call this resdb most probably, and then I will click on the OK button here, and we have tricked the system and we have been able to attach this. Now remember, this is not the original resource DB. We made a copy of it. The original remains intact and is safe. Now in the resource DB, what is stored, if you open up the tables here, you look at the system tables, just wait for that to drill down, you will see a huge list of system tables basically throw up for you. In the same way, you will see a huge list of programming objects which will throw up, which I will drill down for you in a minute. Okay, look at the stored procedures here. That's the stored procedures. You can see here a huge list of stored procedures which are available. System stored procedures. All of these are stored procedures you most probably use, which were created with the product and shipped along with SQL Server, which you can use for various reasons. One of the system stored procedures, which is everybody's favorite, which I'm sure all of you would have used at some point of time or the other, is the system stored procedure called sp_help. You can see all the sp_help stored procedures right here listed for you. You can see here sys.sp_help. Let me script that stored procedure for you and alter to a new query window. And guys, this is a wonderful way where you can get some real good insights into some good ways of programming. If you ever executed a system stored procedure and wondered how in the world is he throwing up these results, what exactly is he doing, you can most probably just go and decode them and run through the code and see how exactly he's getting this information. For example, here you can see sp_help here. You can see what he does and how he tries to give you the information he actually does. And a lot of good programming best practices are things that you can actually pick up from here and learn from here. So I would recommend programmers out there to try and do this. Attach the resource DB, go have a look at all the scripts which I used in those internal system procedures, and pick them up from there. In the same way, if I drill down views, you can see all my information schema views and all those other views which you remember I ran a view earlier, sys.databases. You can see here is the sys.databases. Now if I script this view to a new query editor window, you'll be able to see how exactly was he trying to give me the sys.databases. You can see right now the guy is trying to basically make a huge select statement on a series of tables which are here. You can look at the number of tables that he's actually using here. You can see the sys single objects ref, the sys values, sys p values. You can see all the tables, system views which he's actually querying and tables that he's querying in order to give me the information about all the databases that exist on the system. So in simple, the resource DB, which is a hidden database, is a space where all the system objects are stored. All the system views that we query, all the system functions that we use, all the system stored procedures that we use are all now located in the resource DB. In versions prior to SQL Server 2005, this was stored in the master. All the system objects belong to the master. Due to security reasons, Microsoft have now put this into a dedicated database called the System Resource Database, which is now hidden, which means you cannot run any updates on this particular database. So if you want to modify any objects or you want to add an object in the resource DB, you cannot do that anymore. Okay. If your resource DB gets corrupted, if those files get corrupted, it will bring your system down. Your system will not be able to function normally anymore if the system objects are not available, if resource DB is not available. Now this brings you to a classical question: how do I back up this database? I cannot see it, so how do I back it up? Now you need to do a backup the way I just now copy pasted that data files. That's the way you'll need to do that backup. The good news is you don't have to schedule an everyday backup. You don't have to copy paste this every day or every week or every month. You need to do this only when you basically do a patch update to SQL Server. because the patch update could have updated some of those system objects or could have added a couple of new system objects. So you need to just take a copy of that resource DB only when you do a patch update. If you're not doing this and one day your system resource DB crashes and you need to bring it back again, you will have to go find an MDF, LDF somewhere with the same patch level of the SQL Server instance that is not running anymore because resource DB is down, for you to be able to bring back the system and bring it back to life. So better thing is, if you're an administrator, do make it a norm to take a backup of the resource database, to take a copy of the resource database every time a patch update happens on SQL Server. So that's all the system databases that make this system run, that make this system function. We've got the master, the model, the MSDB, the temp DB, and the resource DB. The most used of all of this is the temp DB, and most of your performance issues will revolve around that. That's the summary of this particular chapter. You have a quiz again which you will be doing. We'll come back once you've finished with the quiz, and we'll go down into one more layer of architecture where we'll understand the database architecture. Enjoy your quiz. SQL Server Database Architecture. The SQL Server database is made up of a series of files. Two files of which are mandatory: the primary data file and the transaction log file. Optionally, you can have secondary log files. A part of the SQL Server database architecture is it's important to understand and remember that we need the temp DB because it is the area in which SQL Server will use in order to store all temporary storage, including any intermediate results of a query, or to store the queries in order to sort them or group them or whatever. So the temp DB is an important part of the SQL Server database architecture. Let's talk a little bit about the primary data file. Now, the primary data file is significant and important because it stores all the system tables which are required to store database metadata. Now, if you remember earlier in this video, we discussed the master database, and we also understood that it stored all instance metadata. Any objects created on an instance, the metadata is stored in the master. But if you create any objects within a database, for example, a table or a view or a stored procedure or a function or a trigger or a user, a database user, the metadata for all of this is stored within that database itself. The primary data file is significant because it contains all the system tables that store the metadata related to that particular database. The transaction log, of course, is used for the recovery process. The transaction log records all transactions occurring on that database in sequence as they are happening in real time. The reason for the transaction log is to be able to recover the data in case of failure, in case of a system failure. Because what happens is, you actually, when you modify data, you are modifying that data in the buffer. You're not modifying the data in the actual physical drives. Now, because the modification of data is on the buffer, what happens with SQL Server's perspective is that you bring a page, or you bring the data that you want to modify into the buffer, you modify it into the buffer. Now, as this modification is taking place, a record is maintained in the transaction log of what modifications occur. Now, these changes in the buffer will go to the hard disk only when checkpoints occur. Checkpoints occur at regular intervals. This can be controlled in some fashions by you setting some properties on the instance of SQL Server. For example, you do have a property called the recovery interval, which in some way governs the frequency of checkpoints. The more longer the recovery interval, the lesser frequent the checkpoints. The more lesser the recovery interval, the more frequent checkpoints would occur. Checkpoints also are triggered by operating system threads called lazy writers, which triggers flushes on buffers, triggering a checkpoint on your database where all changes in your buffer is committed or flushed to your hard drive. Now, the issue here that we need to understand is, in case a change was made to the buffer and the transaction was completed, however, a checkpoint has not yet occurred and a crash occurs, you lose all changes that were made in the buffer. and this would make your database inconsistent. Now, this is where the log file becomes significant, since all transactions were recorded in the log file. When your database starts again, the system will look at the last checkpoint that occurred, which is also marked in the log file, and from that last checkpoint, it is aware that all transactions after this were not committed to the hard drive, were not written to the hard disk. So it would redo all the transactions that were completed, and it will roll back any transactions that were incomplete while at the time of the crash. So a roll forward and a roll back occurs on the transaction log, thereby bringing your database back to the previous state of consistency. So that's the value of the log file. Now what we're going to do is in this session, let's have a look at a small little demonstration where we'll try and figure out how the database primary and secondary data files are actually used. We will then also deep dive into the page architecture, where we'll try and understand how pages are stored and organized inside these data files. Let's start off with a demonstration on understanding the data files themselves. So switching over now to our SQL Server Management Studio, which I already have open. Just do a cleanup from the previous demonstration there. That's not deleting, because this is another thing which is important. You cannot drop a database while connections are open to it. However, if you close connections, you will be able to drop it like you've seen me right now. Click on that checkbox. Let's go ahead and create a new database right now for this demonstration. I'm going to call this database data DB arc. So that's for database architecture. Now this is the primary data file, which you see is mandatory. You can locate it wherever you want. You can change that path. The file name is not there, but the file name by default will be the same name as the logical name, and it will have an extension of .mdf, a primary data file, MDF. Now, since I've already told you that the significance of the primary data file is it stores the metadata related to the database, I'm going to rename this logical name of the primary file to metadata. I'm going to add another file here, which I'm going to call data1. Now, SQL Server files can be located or can be grouped together in what is called file groups. In fact, when you're talking about the system and you want to create objects, objects need to be created on a particular file group, and you cannot create them on files. You can only create them on file groups. So the file groups plays a significant role in the database architecture. So what I'm going to do right now, I'm going to create a new file group. You cannot do this for the primary data file. You notice the primary data file can only be located on the primary file group. I cannot change that there. However, when I created data1, data1 is a secondary file, because every database can have only one MDF, only one primary data file, which contains those the set of those system tables, which will store the data metadata related to this database. So I'm going to create data1, and I'm going to create a new file group for it, which I'm going to call the data FG. I'm also going to make this the default file group, which means that if I create any object and I do not specify which file group I want this object to be located on, it will automatically be created on the data FG file group. That's what setting the default here means. So data FG, which is my file group, becomes my default file group, where I've got a single file called data1, which is a secondary data file. I'll click here on OK to have this database created. And once this database is created, I'm going to right click on databases. I have some problems retrieving information there. Let's see what happened. I'll troubleshoot that in a minute. Okay, that was just a connection issue. So we've got the instance back. We're connected. I've got this DB arc right now here. I'm going to right click on DB arc. I'm going to click on new query here to create a new table, and I'm going to type in that syntax here. I'm going to say create table. Let's call this table X. I'm going to give it one column called column1, which is going to be an integer data type. I'm going to create a second column, which I'm going to give as a char data type, and I'm going to put in here as the length of that character as 5000, which means this would effectively take around 5000 bytes of storage, this column. 4 bytes goes for the integer data type, which is there. So if you're really thinking of it, 5004 bytes is the size of my row. SQL Server, whenever you insert data into this, will have an internal overhead of around 4 bytes. So you're most probably looking at 5008 bytes taken in order to store a row in this table, or when I insert one, that is. Now I've not specified on which file group I want this table created. So when I create this table, it will get created on the data.fg file group, or which, if you remember, was our default file group. Before we go ahead and create that, I'm going to go to the reports button here. I'm going to go to the standards report, and I'm going to pick up the disk usage report. Before we created anything on this database, let's have a look at what is the space being used by the two data files which we currently have. Now we have two data files here, one called metadata and one called data. You can see both of them listed right now here, and the data one, you notice the space used is 64 KB. Now this is 64 KB because by default, every file that you create on SQL Server, there are six pages in this file which is required for internal housekeeping. So each page is 8 KB in size, so 8 pages. 6 pages. So sorry, a lapse of concentration there. 8 pages, okay. 8 consecutive pages, okay. Each page is 8 KB. So that's 64 KB is basically used by the system internally for housekeeping. So any new file you create, you can be sure of one thing: 64 KB will always be taken, and this will be used internally by the system. My primary data file, of course, is pretty larger because this has a series of system tables already created on it. Now the size of this file and the space used here, if you remember, we create this using a copy of model. So it totally depends on what the size of model's primary data file is. That's what space is being used in that model, because when you create a new database, it's simply a copy of model. So that's what determines this size. So a series of system tables are already there on this primary data file, and it contains currently it's using a space of 2.44 MB. I switch back to this window and I create table X. Now when I create table X, the interesting thing here to understand is that it never touched my data1 file at all, because when you run DDL commands like create table, alter table, drop table, you are effectively creating metadata. You create a table whose name is X. So what would happen is you would have an entry being made into one of the system tables called sys.tables. So where name is equal to X. Now if I run this command, this of course is a metadata view. We cannot see those tables or query those tables directly anymore in SQL Server. So I'm using the view, the metadata view, and you can see here I've got one record created for the table called X. So this system table is located on the primary data file. I also have another entry, most probably, which has taken place in the table called sys.columns. So let me just pick that up. I'll pick up sys.columns, where the ID, I cannot use where the object underscore ID is equal to, I'm going to use a function here called object underscore ID, and I will give in the name of the table, and this function will automatically get me the ID of that object, and I can run this query now, and I would see two rows here, one for each column, the column call1 and the column called call2. So these are the system tables, these are the metadata tables which I was referring to, and these tables are located on the primary data file. So when I executed that command, the only file that got affected was the file which we call a metadata in this particular demo. One more interesting table that you can actually look at. This is a backward compatibility view, which I'm showing you. sys.sysindexes. I'm going to pick up that again, where I'm going to say where object underscore id. The backward compatibility view does not have the column called object underscore id. It's called id there. So I'm creating the sysindexes backward compatibility view, and I'm picking up the details of x. At this stage, it's interesting to note some values which you will see here. One of the values which I would like you to basically look at is the value in the column called first IAM. I'm going to just copy that. I'm going to paste that here in a comment so that you will remember what value it had. And also at this stage, it's interesting to notice that the D pages value is 0 and the use page value is also equal to 0. So this particular table is currently using 0 pages. And of course, 0 pages, it's totally using 0 pages, which means there are also no data pages. So there are 0 data pages and 0 used pages currently being used by this table. Our disk usage has not touched data 1 at all. Data 1 will still remain at 64 KB, which is used by the system internally, and you'll see no expansion at all in the space used here, because this query which we ran, the create table command, never had any impact at all on the data 1, because all you did was just now create metadata. However, I'll go ahead and make my first insert into this table. I'll say insert into x values 1 comma, I'll put in some text there, 1 comma BC or whatever, but if you know, that column would still take the size of 5000 bytes because it was a char 5000. Now I make that first insert here, and before I show you the report again, let me show you the sysindexes table, which says that we are using 1 data page and the total pages being used are equal to 2. Now the 2 used pages here are because when a table is created and when you try to insert data into the table, before we find a data page to store that data, we need to find one page which acts as an index allocation map, which is an IAM page. Now this page will store the details or the addresses of all the data pages that belong to this table. In fact, that's how you will come to know tomorrow, if you have to read data from X, you will need to find all the pages that has data related to X. Now this you will be able to find from the IAM page. So when the table is new, it does not have an IAM. So when you make the first insert, one IAM page will get created and one data page will get created to actually store the data you're inserting. Now the other column which I would like to show you now is, I will go back to this first IAM, I will paste that right here and show you that now you've got a valid value inside this first IAM. Now this is the address of the IAM page, the index allocation map page that belongs to X. So guys, it's as simple and straightforward as this. If I want to read data from table X right now, I need this address first. So I go to the sysindexes, I pick up this address, I go to this address, and this is a page, and this page contains this page is the IAM page for the table X, and on this page I will find the addresses of all the data pages that belong to X. In this case, there's only one data page that belongs to X. Now this address that you're looking at here uses the reverse 2-bit algorithm. So if you want to really break this up, is you need to remove the 0x, because 0x actually here means that this is a hexadecimal value. I'm going to then split this into 2 bits because that's what how the algorithm works, and then I'm going to reverse it. I'm going to reverse these 2 bits, 00, 03, 00, 00, 00 again, and 09. I'm now going to split this after the first 4 values. Now what you're effectively looking at is file number 3 and page number 9 is the address of the IAM page that belongs to this table. I don't need to convert this from hexadecimal to decimal right now, because 3 and 9, the decimal and hexadecimal values are the same. Otherwise you would need to do that conversion to get the right page number and the right file number. So this is the address, the first IAM that belongs to this particular table. And the good perspective is here now, this particular IAM page could track up to a series of pages, and whenever a new page is required, a new page will get created where and when required. A new IAM page will get created if this page is full and it cannot store any more addresses of data pages that belong to this particular table. So that's what really happened. Currently, we are using two pages. That's around 16 bytes. So you can see here the pages used is two. The data pages are only one. One is an IAM page. If I come back to the disk usage now and refresh this report, you will see that data 1 is now being used because this table was created on data FG file group, and data FG file group was having a file called data 1. You can see now the space used is increased by 64 KB because that's the allocation of the operating system. So you've got 64 KB chunk which is given to you. However, you are currently using only 2 pages in those 8 pages that were given to you. I'm going to make a couple of more inserts here. 1, 2, and 3. I make 3 more inserts. I check my sys indexes. Sorry, I think I made the 4th insert also there right now. I check my sys indexes, and we've inserted 4 rows in this table so far. And you can see the data pages are equal to 4. Now the reason for that is because our row size is 5008 bytes. A page can hold data up to 8060 bytes only, because rest of the page space is given away to what we call the page header and the page footer. So 8060 bytes of space, we are using 5008 bytes there already. The remaining 3000 bytes cannot fit the second row. So the second row goes onto a second page. The third row goes onto a third page. Because another important concept for you to understand here is that a row cannot span pages. A row can either fit on this page or it cannot, it goes to a new page. You cannot store part of the row on this page and part of the row on another page. That's something which is not possible. So because of that nature, every row we insert currently will be a new page. So currently 4 rows means 4 pages, and total use pages are 5 because there's one IAM. And now I think you could visualize what this IAM has. This IAM has the address of these 4 data pages. Now how do you find the IAM? Where is the IAM? Now to find the IAM, you go to the column called first IAM and pick up the address from there. Now it's as simple and clear as that. If you look at the disk usage right now, we are using 5 pages, but so 8 pages were given to us, so you don't have to worry about that anymore. You will still see the space used here at 128 KB because we still have another 3 pages which we have to use before the system tries to give us more space. So I'm going to do that now. I'm going to make a couple of more inserts here. One more. That's pages used now is 6, 7, and 8. Now if I check the sys indexes, I should see the page space used, pages used is equal to 8. If I check my disk usage report, this would still remain at 128 KB. However, we are now using all the 8 pages that were given to us by the system, by the file system. So it's still 128 KB, and currently I'm using all the pages. I'll go back to this query once more and just insert one more, make one more insert here. And this one more insert here would change the pages used to 9, and this now means I've already used up the 8 pages that I had, and you will see this jump now by another 64 KB. Yeah, you are. This is now 192 from the 128 which it was earlier, and you can go on inserting this way, and this will go on increasing, and that's how it actually works. Now taking you back to my PowerPoint deck here. We will try and understand a little more about how this really works. Every file of yours, data file, is broken up into 8 KB units, which are called pages. 8 consecutive pages is called an extent. Now we're talking about the page architecture. Actually, we are moving from database architecture to the architecture of the file itself. So the files are broken into 8 KB chunks. Each 8 KB chunk is called a page, and 8 consecutive pages is called an extent. Now, there are two types of pages: pages that are used by the system internally to track space allocation, to find out how much space I have, and who I've given pages to, who I've not given pages to, as have pages been allocated, if they've been allocated, who have they been allocated to. So there's a set of pages just to track this information. And apart from that, there's a set of pages which will actually store your data and your index information when you create indexes. Now, extents are also of two types. You have mixed extents and you have uniform extents. Mixed extents happen to be when the 8 consecutive pages are storing data that belong to different objects. It's called a mixed extent. Mixed extents could also have free pages in them, but they would still be mixed. Uniform extents are when 8 consecutive pages are having the same kind of data, or all 8 pages are not being used. In this case, it would be called a uniform extent. Now, 8 consecutive pages having same kind of data will be called an allocated uniform extent, and 8 consecutive pages which are free and not been allocated would be called a free uniform extent. Now, these extents are used in order to basically find pages and allocate them to your objects. Now, how that really works is we do have the first 8 pages. If you remember, I'll just come back to how extents are used on my next slide. We spoke about the first 8 pages being used by the system internally. Now, I'm giving you 4 of these pages. The first of the pages is a file header, which stores information about the file itself. The second page is a PFS page, which stands for Pages Free Space. Now, what this stores is, it stores the address of every allocated page with a bitmap indicator indicating the percentage of free space. So the concept here is very simple. If I want to insert data on a particular page, before I really try that insert, I would like to know if there's enough free space. So I'll go to the PFS page, which is hard coded as the second page of every data file. So I'll go to the PFS page, search for this page address, look at that bitmap indicator to find out how much space is available on that page. And if there's enough space to insert the record I'm trying to insert, I will go ahead and put it there. And if there's not enough space, then I will most probably need to find a new page. So that's what the PFS is used for. More PFSs will get created as and when this PFS is full. A single PFS can track up to 8,000 consecutive pages. I think it's 15,000. Please just check up your documentation on those numbers in case I'm wrong on them. The third page of every data file is a GAM page. GAM stands for Global Allocation Map. Now, the Global Allocation Map stores the address of uniform extents. Now, you know what a uniform extent is. 8 consecutive pages that are storing the same kind of data, or 8 consecutive pages that are completely free, is called a uniform extent. GAM stores the address of every uniform extent that has 8 free pages. In other words, a uniform extent that has not been used. 8 consecutive pages that are free. The address will be on the GAM page. Again, new GAM pages will get created in case this page gets full as and when required. However, a single GAM page has the ability to track up to 64,000 extents, so that's a large number. Still, in case you have larger files than that, more GAMs will get created as and when required. The fourth page of every data file is an SGAM page, which stands for Shared Global Allocation Map. Now, what this guy stores is the address of every mixed extent that has at least one free page. So for the address of the mixed extent to be on the SGAM, that particular mixed extent has to have at least one free page. Now guys, this is the file architecture. I remember showing you 64 KB already being used, the first 8 pages of a file, the first 4 pages, what they store is relevant to page and space allocation. The other 4 are related to various different things. We'll talk about them maybe in the other sessions when we come to topics related to differential backup and so on, or bulk operations and differential backups and so on, because that's what these other pages would track. But the first 4 pages are all about space allocation. And this is for every data file. Every data file, first 8 pages are taken by the system. The first page of that file is a file header. You know what it does now. The second page is a PFS page. You know what it does now. A GAM is the third page, and an SGAM is the fourth page. Now, how are all of this used? Now, when I created the table, nothing really happened because the only thing that happens is metadata gets created. When I try to make the first insert, two pages get used. One page, which becomes the IAM page for that particular table, and one, a data page. The system tries to find these pages from mixed extents, which have free pages. The system will get these mixed extents, will find these mixed extents that have free pages by going to the SGAM page. So the SGAM will point the system to the nearest available mixed extent that has a free page, and the system will go there and allocate that page, first an IAM page for the table, and once the IAM is allocated, it will then go searching for another mixed extent which has a free page, and it will allocate a data page where it inserts that data. So currently our blue page here is the data page, our purple page here is the IAM page. Our blue page here is the IAM page, our purple page here is the data page, and the address of this purple page would be stored on this blue page. And the address of the blue page will be stored in the sys indexes table in the column called first IAM, as I shown you earlier in the demo. Now, as you start inserting new rows, the system will go to the IAM page, find this purple page, go to the PFS page, find out if this purple page has space. If it has space, it will insert the record. If it does not, it will search for another data page, allocate it, and put that address also on the blue page. Now, this system continues of allocating data pages as they fill until 8 consecutive pages are full. Now, storing data in this kind of a manner is, we refer to this as we are storing data on a heap, because there is no defined sort order of your rows which are being stored in these pages. So currently we have 8 data pages. You've got 8 purple pages on my slide. So 8 purple pages now are occupied with rows of data, and these rows are stored in what we call a heap. There would be 8 addresses on the blue page pointing to these 8 data pages which belong to this table which I created. Now, when I try to make another insert, instead of giving me one page at a time, because see, the method of allocation so far was one page at a time. The system would go to the SGAM, it would find a mixed extent that has a free page, and it will allocate that particular page, one page, to the table. Now, this was the allocation method for the first 8 pages. Once 8 pages are full, the system will now go to the GAM, and the next allocation would be a uniform extent with 8 consecutive pages. So it will allocate 8 pages at a time. That's how SQL Server allocates pages and stores data on those files, data files that we actually use. Now, how the transaction log works, you've already seen. So let me just take you back for one final demonstration here on understanding file groups and pages. I have this problem always when I come back to my VM. I just reconnect to that in a minute. So I'm reconnecting back to my virtual machine. This virtual machine was created on Azure. I encourage you guys to go do that. It'll just take you a couple of minutes. Set up an Azure account and create a VM using the SQL Server 2014 template, and you'll get an image created with SQL Server already installed and up and running on it. What we had done earlier was we created this particular table called X. I'm going to do something now. I'm going to drop this table X. And I'll go to the properties of my DB arc. I'll go to files, which is here, and I'm going to add a second file, which I'm going to call data2. This will also be a secondary file, and I'm going to keep this on data.ifg. I'm going to add a third data file, which I'm going to call data3, which I'll also keep on the data.ifg. Now, guys, the order of creating this was, the first file I created was data1, the second I created was data2, the third I created was data3. I click here on OK to get this created. And just before we do anything else, let me show you the disk usage report now. The disk usage report here would tell you that data1, data2, and data3 are all having only 64 KB used. And now you know what that 64 KB is. We spoke about that. Because we have no user tables created. If you remember, I dropped that table X, so it was using data1 while it was there, but after I dropped it, the data is not, nothing is being used. So we've got 3 new files, data1, data2, and data3. all three of them located on the same file group data fg. Interestingly, now when I create this table, it still gets created on the data fg file group because that was the default file group. But when I make my insert now, the interesting thing is there is going to be a challenge in terms of which file will I use, because see, the table was created on the data fg file group. The data fg file group has three data files: data 1, data 2 and data 3. So the question here which will get created would be is, which file do I use? Let's have a look at this. So when I execute this command now, my sysindexes will show me just like earlier that two pages are being used. Nothing changes there at all. One IAM page again, one data page, one IAM page, two used pages. Now I go back to my disk usage. I click on the refresh here, and by default the system will use one of the files first. Now the file that he uses first is the file which has the max file ID, and the max file ID will be the file which I created last naturally, which was data 3. So you can see data 3 now has 128 KB used. So this is what has been picked up, and data 3 is being used. Now I'll continue my inserts on this table. I'm going to insert 7 more records. 1, 2, 3, 4, 5, 6 more records. Sorry. Now after 6 more records, my D pages are 7. I had inserted 1 record earlier, and my use pages are equal to 8. At this stage, my data 3 is still 128 KB, but now I'm using all those 8 pages which were given to me from data 3. Data 1 and data 2 are not yet touched. I go back to my query here, and I make one more insert into the system. And now, since he's already used data 3, he will now use the next, he use the file with the max ID first. He'll use the file with the next lower ID. That is, in our case, that would be data 2 to insert this record. If you're looking at the pages used in sysindexes, you will see 8 data pages and 9 used pages. So you're still having 1 IAM. I go back to refresh this report, and now you will see data 2 also would have 128 KB used in it. The system will continue to round robin this. So once this 8 pages are used, it will then basically go and use data 1. Once this is done, it will come back to data 3. So it's going to be a round robin this each of these files using 3 of them. The great thing here is, in case you already had data 1 was large and already lots of space used, and if data 2 and data 3 were smaller in size, then the system will round robin only between data 2 and data 3 until it makes data 2 and data 3 catch up with the space used of data 1. And then it will go back to round robin between all 3 of them. In other words, the system tries to maintain the same size in all the files being used by this particular object. Data is split across these files, and it tries to maintain the same size for all the files involved. Now, why do we need to use this? Just imagine for a few minutes if data 1, data 2 and data 3 were put on physically separate hard drives on your machine. It would mean whenever you read data from table X currently has data on 3 different drives, C, D and E. You would get the benefit, the performance benefit of a complete parallel I/O, where the system will be able to read from 3 hard disks at the same time to fetch the data required for you in order to give you that data. Now that's the benefit you have in creating file groups. Best practice recommendation here is always create a secondary file group for your user tables. Do not create your user tables on the primary file group. Leave the primary file group and the primary data file alone to manage the system tables excuse me, and the metadata related to the database. Use file groups to improve performance by ensuring you have parallel I/O, especially if you're having disk bottlenecks and you're having I/O issues where you're having disk read waits happening on your system. It would be the easiest thing to do is introduce a couple of more disks and ensure you split your data across multiple disks by creating multiple files on these disks and linking them all to a single file group. Now that's the concept of databases, data files, file groups, and the log files. I hope you've understood primary data files, secondary data files, and also log files, as well as understanding pages, GAM, SGAM, PFS, IAM, that's the index allocation map, and how these pages are actually used in the entire system. The last architecture we'll be doing in this particular series would be, we are going to talk about the page itself. So I'm going to talk about how the page works. Now, pages could store data, it could store indexes, it could store blobs like image and text data types when you use. You also have pages which are specifically meant to store some specific kind of information, like the GAM pages, which is the global allocation map, which we've already spoken about, the IEM page, which are the index allocation maps, PFS pages, which are the pages free spaces, the bulk change map, which we haven't spoken about in this session, and the differential change map, which we also haven't covered in this session. So these are the different types of pages you could land up talking about when you're working with the SQL Server pages. Now, how data itself is stored on a page is also a complex mechanism which is used, because see, the great thing about relational databases is the segregation it made between the actual data that you want to store and the metadata about that data. So today when you're storing data, you're just storing data. You're not storing commas to delimit columns. You're not storing column names. You're not storing data types. You're just storing data when we talk about data. Now, this would also mean that there should be some mechanism of how you can map your column names to the data that you're reading, because the column names are stored elsewhere and your data is stored elsewhere. No segregators, no delimiters are telling you where the values for one column is starting and where the other one, and where it ends. So data, or rows of data, are organized on your pages like you see in the diagram here. Every row has a header which takes 4 bytes. That's the overhead we spoke about earlier in this session. So 4 bytes overhead for every row, and this would have header information. And at the bottom of the page, every page will have a footer which has a pointer to this header, which we refer to as the row offset. So how do you find a row on a page? You go to the bottom of the page, which is the row offset, or the page footer. You find the row offset there, which is pointing to where on this page is the starting of the row. So the row offset here helps you segregate one row from the other row, because you're able to pick a particular row by finding the position of that row on that page by looking at the row offset, which is stored in the footer of the page. So this header is something which is important for every row. So first you have a 4 bytes header for a row, and after that it's followed up with all the data that have fixed data types, because in this way you don't need delimiters to segregate these columns. You could pick up these columns because they have fixed sizes. A char 5 will have 5 bytes, so you say great, this column is 5 bytes, the next column is 7 bytes, the next column is 10 bytes. So it's going to be as simple as that when the data is fixed. So first it stores all the fixed data. The problem here you would have is with null values. If one of those fixed data columns was null, it means you need to skip reading it. It means the data for that column does not exist. Now, how would you know which columns were null in this row? Because the null columns here could vary from row to row. So we have a nullability block straight after that, which uses 2 bytes to store the number of columns which are null, and uses a single nullability bit for every column that is there in the row, specifying whether for this particular row, whether that value was null or not null, a 0 or a 1. So a nullability bit is here specifying which columns are null and which are not. Whichever column has a 0, which says that this column is a null value, or it would automatically, the system would know that this column should not be mapped when it is trying to map the metadata for these columns. It needs to leave out the second column because the second column does not have data. So it will give you null for the second column because the system here, the nullability bit here, told him the second column was a null value. Straight after the nullable block, you have the variable block. Storing variable data is challenging because the length of it varies, and since we have no delimiters, how are we going to know when the column ended and when a new column started? The variable block solves this problem for us. 2 bytes are taken here to store the number of variable length columns in this row, and another 2 bytes is taken for every variable length column. 2 bytes would be taken where it will give you a pointer to the end of that variable column. In simpler words, it will tell you what is the size of the data in each variable column that you actually have in this row. So 2 bytes of overhead there, plus of course the system needs to find this out dynamically because this varies from row to row. So using a lot of variable data types in your columns, in your table columns, may not really be as good and great as the way it sounded. It comes with this overhead, remember that. However, this overhead normally we tend to believe that this overhead outweighs the amount of space we'll be saving eventually because of using variable length data. So if you need to put something as a varchar 20, and if the average size of data which is going to come into that column is around 10 bytes, you most probably are saving 50% of space, which would have taken if you had to say char 20 instead. So this is a good amount of space to save, and you don't mind this overhead which you're looking at. However, if you have to say varchar 20 and the length of the data in this case was going to be an average of around 18 bytes, and you thought you were going to save 2 bytes, then I don't think so you're going to save anything because the internal overhead will outweigh the benefits you're actually getting. So that's a word of caution for those of you who are using varchar or nvarchar. Just remember they come with overheads, and we need to see significant space saving benefits to be able to accept this overhead, which actually happens. So that was the last part where we store the variable data, and that's your page architecture too. So what we actually covered for you in this module right now is I've tried and covered for you the database architecture, the file architecture, and also the page architecture, where you've understood how rows are stored on the pages. You also are aware that pages have headers, which are, I don't know if I mentioned this earlier, so a page has a header which takes 86 bytes. It takes some space for a footer, which stores the offsets of the rows, and it has 8060 bytes available for you to actually put your data values on the system. In Microsoft SQL Server, you cannot change the size of the page. In Microsoft SQL Server, a row cannot span pages. You cannot put some part of the data on one page, some on the other. Yes, that is done internally by the system in a new overflow page, or when in some scenarios which we are not discussing in this particular video, but yes, before I really say that you cannot span rows across pages, there are scenarios where this could be possible using overflow pages, but not discussing that scenario. You can most probably do some further reading on overflow pages to understand. That was introduced in the 2008 version of SQL Server, so you can most probably have a look at it and see what overflow pages are all about. But in summary, your row size cannot exceed 8060 bytes, excluding of course binary large objects, because those are stored as B trees. And secondly, rows cannot span pages. Page size is 8 KB, 96 bytes header, some space goes for the footer, and 8060 bytes is what is available for you for your data to store. You have a small quiz on this, and once you're done with that quiz, I'll talk to you a little about indexing and how indexing works. We have another video coming up on in-depth indexing, so we'll do much more on that. So I'll just talk to you a little about indexing in this session before we actually wind up. See you after the quiz. The last topic that we're discussing in this video is about indexes and how indexes actually work. This is a brief on the same. Now, one way which SQL Server could use to get data from your system is what we call a table scan. Now, in a table scan, SQL Server will read all the pages that belong to the table. And to find all the pages that belong to the table, you will use the index allocation map. Even if you wanted to read just one row out of a million rows or a billion rows, SQL Server will still go to every single page that belongs to that table. This is what we refer to as a table scan. Alternatively, when you want to find a particular row, instead of scanning all the pages, you can use an index and search for that particular row and find the address of the page on which that row is located. And then you can go to that page and read that record. So the second method of reading data is to use an index to find the rows. So either you can read all the data pages doing a table scan, or you can use an index in order to find only the rows that you want and only go to those pages. Now that's how SQL Server assesses data. Now, when you're talking about a table scan, you definitely are sure of one thing: your table is stored in what is called a heap. A table that does not have a clustered index is called a heap. The pages for this particular table will have no particular order, and the rows on these pages will also have no particular order. The system is able to find all these pages only because it has a page called an IAM page, which keeps track of all the data pages which are there in the heap. So it uses the IAM page, goes to all the pages in the heap, or reads the data from there and gives you the desired result. A clustered index is where we have a root page. The root page could have intermediate pages, and then you can further have leaf level pages, and in the leaf level pages you actually have the data row. So if I was trying to find a customer whose ID was equal to 5, the root page, I would navigate through the root page searching using the B tree search until I reach the particular data page where customer ID 5 is located. To find the root page of the index, we have a column called root page in the sysindexes table, or we would go there, we'd pick up the address of the root page, and we would start searching for this customer ID from the root page, and we will navigate downwards until we reach that particular data page where that record is located. This is a clustered index. There could be intermediate pages too, depending on the number of records and the size of your table. The third method, we can also pick up data using a non-clustered index. Meanwhile, you're just looking at that navigation there, how the system from the root page navigates to the possible intermediate pages and reaches the necessary data pages. Those red arrows showing you connections there. If I go to one leaf page, I can from there go to the second, the third, the fourth, because I have both forward and backward pointers about pages which are there in the clustered index. In a non-clustered index, it's very similar B tree towards what you've seen in the clustered index. You still have a root page, you still have leaf pages, you still could have intermediate pages. The only difference here is the index leaf node does not contain data. It just contains a key and a pointer to data. So the clustered index, well, is when you reach the leaf page, you actually got the entire row there. But in the non-clustered index, when you reach the leaf page, you only have a key value and a pointer to the actual data page. Now, the data page could actually be located on a heap, or it could be located in a clustered index. The non-clustered index will only give you a pointer to where the row is located. So if you're searching for customer ID 5, when you reach the leaf node of the non-clustered index, it will tell you customer ID 5 is located, the row for customer ID 5 is located here. So you'll need to pick up that address, go to either the heap or navigate through a clustered index and get that particular data page and retrieve your results. Now, the interesting thing about SQL Server, this is navigation through a non-clustered index, is that non-clustered index you could have as many as equal to the number of columns you have in SQL Server 2008. You could have up to 249 non-clustered indexes on a table. That has increased in the later versions. And as far as the clustered index is concerned, you can have only one. So that's an important thing to remember for the indexes. We'll be doing one more video on in-depth on indexes, so we'll talk more about it in that. With that, we've come to an end of this particular video session, and hope you've understood the architectures of pages and extents and files and file groups and communication architecture, where you understood the tabular data stream protocols and so on. Thank you so much for attending this session. We appreciate the time you've taken out. Hope you got some value learning from it. Thank you all once again. Hope to see you in the other video sessions.